class. So last class we did with started with assemblers and a few things we discussed. We shall continue this and see the implementation of assemblers, two-pass assemblers. That's what is the thing. So in the previous class, we just came to know that the assembler is a software which takes the assembly language program, converts it into reallocatable object code using the instruction set of the machine as well as the addressing modes. Fine. Quick recap. Assembly language programs are made up of three types of statements. Imperative statements, which does the action, called as instructions also, which is going to have the instruction, mnemonic, as well as the operand. Declarative statements, which are usually specified as assembler directives, RESW, byte, word, RESB, like this, which are usually the declarative statements assigns the memory. It doesn't be converted into object code. The third type of statements are assembler directives, which are instructions to the assembler itself about how to assemble the program. Right? They will also not be converted into object code, but they are the guidelines to this. And any assembly language statement will be having three parts like this: label, mnemonic, as well as operand. After assembly, the label and the operands will be converted into address, and the mnemonic will be converted into output. This much I think we have completed. We shall proceed further. This also we did. SIC assembler, these are the following functions an SIC assembler does: convert the mnemonics to opcode, symbolic operands to addresses, data constants to its representations or the values, and resolve the assembler directives, and finally write the object code into the appropriate file format. So these are the tasks that your assembler does. Right. We have seen this also. Two-pass assembler will go two passes on the given program because SIC program, SIC programs are written in such a way that the declarations appears later, but the instructions appear first. So first pass is a definition pass wherein we'll assign addresses to every statement in the program and resolve some assembler directives. And this is the task what we do in pass one. That's what we call it as definition pass. But in the second pass, we'll actually do the translation. Means in the second class, we're going to convert all the mnemonics to opcode and all the operands to its addresses, the same addresses which are being generated by your pass one. The symbol table entry will be made in pass one. The symbol table reference will be made in pass two, right? And it processes the other assembler directives which are not being done by your pass one, right? And finally writes the object code into appropriate file format, right? Yeah. As I told, when we want to implement the assembler, we need some three data structures. Well, first one is symbol table, second one is opcode table, third one is location counter, which is an integer. These are the three data structures that is used. And this is one of the usual question in the examination that will be asked. Right about the data structures that is used for implementing two-pass assemblers or SIC assemblers like this. Usually commonly asked question is this. So first one among them is a opcode table, which we call it as optab. Optab contains the opcode in hexadecimal format. So for each instruction, all the instructions of a particular SIC machine and SICXC will have a concerned opcode written in hexadecimal. That's what is your opcode table contains. Right. In pass one, we'll just check the opcode table to validate whether the instruction which you have written in the program is a valid instruction or not. But in pass two, we'll use this value or the opcode so as to replace the mnemonic. The mnemonic is something like jump subroutine is there. Jump subroutine JSUB will be replaced by its appropriate opcode. This is what will be done in the pass two, right? And we implement, and the opcode table is a read-only table because the instruction set of any machine architecture is fixed. You cannot add or you cannot remove. So it is a read-only table. And only, next one is opcode table is arranged in the form of a hashtag. The reason for this is the search need to be quick. For that reason, we are going to organize the opcode table in the format of hash table. Right? This is what it is. Right. Here you can see on the screen the opcode table of SIC machine. For all the instruction, data transfer, arithmetic, branch, IO, everything, we have the instructions and their concerned hub. Something like here add is 18H. 18H means 18 is the opcode. H indicates the hexadecimal. It's not 18H. It is 18. That's it, 18. Similarly, JEQ is having 30, which is in hexadecimal, right? So why is it so we are using hexadecimal? The output of your assembler will be a total hexadecimal thing, which will be converted into binaries by a hexadecimal to binary converter. That's it. So the output from your assembler, that is the object code, will be in the hexadecimal format, not in binary. Okay. The hexadecimal to binary converter will do the rest of it. Right? This is the opcode table of SIC machine, not SICXE. This is the opcode table of SICXE. I think I have shared you this particular document already on the group. You please refer to this. This reference is very much needed when we are assembling each of the code in the further exam. You don't need to by heart and remember this. See, usually the question will be, I told you about the data structures they're going to ask. You don't need to write the entire, what you call, opcode table. You can write some few examples, that's enough. And when we are assembling the program, for the program or the code snippet which is given in the question paper, they would only have given the appropriate opcode so that you can use them and assemble. So you need to know the procedure, not the values. You don't need to remember the values. This is a SICXE opcode table, and here is some of the instructions, something like sub F, which is a floating point subtraction, whose opcode is 5C, like this. Okay. Yeah. Next is symbol table. As usual, we know symbol table contains the user-defined symbols and its attributes. The same here contains all the user-defined symbols and its addresses. This symbol table will be populated during pass 1 of the assembly. What actually happens in pass 1, we'll assign addresses for each instruction and each declaration. That's why it is called a definition phase. This, whenever the address is assigned to a user-defined symbol, means user-defined symbol that is appearing towards the left-hand side. User-defined symbol appears on the left-hand side only if it is a declaration. Point number 1, if it is a declaration of a constant or a variable. Second one, it should be a label. So go to label. It should be a label. So all in these two cases, the symbols will appear towards the left-hand side of a mnemonic. So wherever in the pass 1, wherever when we are assigning the addresses, wherever the left symbol, user-defined symbol is appearing towards the left-hand side, those symbols along with their addresses will be entered into a symbol table. So symbol table populating will happen during pass 1 or in the definition pass of the assembly. Right. During pass 2, we need to do the conversion. Means we will take the address of the symbol from the symbol table and replace all the operands or all the user-defined symbols that is appearing towards the right-hand side of the mnemonic. Right-hand side is the usage or used as operand. Symbol appearing on RHS is an operand. So that will be replaced by the appropriate address. So this is what happens with the symbol table. And the symbol table is also organized in the form of a hash table so that the reference can be faster. The last data structure what we use is location counter, LOCCTR. LOCCTR is an integer variable. This is used in pass 1 so as to define the addresses for the symbol. Define the addresses for the symbol. During pass 1, it is going to allocate the addresses. It will be initialized with the value, whatever is specified beside the assembler directive start. Start indicates beginning of the program. If an address is specified, for example, 2000 is specified, it indicates that every first instruction of this program will start from the address 2000 and it continues. Each instruction, if it is 3 bytes, next will be at 2003, next will be at 2006, and so on. It will go on. That's how. Right. After each statement, the location counter is incremented by the size of that particular instruction. In SIC, all the instructions will be of 3 bytes, 24 bits. But this may vary in SIC XE. Also, if at all a statement is not an instruction and if it is a declarative statement, the location counter will be incremented by the size of that variable or a constant. Okay, that we're going to see next. And every label on LHS is entered into the symbol table along with its address. That's what is the 3 data structures that we use with implementation of 2-pass assembler. One of the important questions that usually will be asked in your examinations. Fine. The next we have the algorithm for implementation of SIC and SIC assembler. We don't have a separate algorithm for SIC XE, but the distinguishing features from SIC, what and all are there, those will be handled or addressed in machine dependent and machine independent assembler features. So for that reason, we don't have a separate algorithm for SIC XE. We have only the algorithm for SIC. We have 2 algorithms, that is pass 1 algorithm and as well as pass 2 algorithm. One of the important question again is writing the algorithm for assemblers. Usually they don't ask you to people to write pass 2 of 2-pass assembler. Majority of the times they have asked you to write the pass 1 assembler algorithm. Pass 1 algorithm for 2-pass assemblers, right? Usually, and you don't need to head this algorithm. The algorithm is quite simple. You don't need to remember a few points. You can create the algorithm by yourself. Right? Let's browse through it and understand. Simple way. Whatever I told you in the text is been written in the form of algorithm. That's it. Okay. Begin and if read the first line of your program. If the opcode is equal to start, means if the first statement is containing a start, then this code block that is between begin and end is supposed to be executed. What we are trying to do? Save the operand, that starting hash operand. Hash operand means the value that is specified in the place of operand, right? That's what is the thing. For example, I have written string start 1000, means string is the name of the program, start is the assembler directive, 1000 is the address from where the assembly is supposed to be started. That value 1000 is supposed to be put into your what you call symbol table. So for that reason, location counter will be initialized to that particular value, and that value will be put into symbol table, right? And then we'll go on reading the next line, right? If suppose operand is not given, you have not given the address beside your start, then assembler by default will going to start from the 0, 0. So location counter will be initialized to 0. That's what we have written in the else part of the program, right? Okay. Next one is until you are supposed to do the rest of the things until what? Opcode not equal to end. Until the program ends or you find the assembler directive end, we should keep on doing. What we are supposed to do now? We should allocate addresses for all the instructions. We should also allocate the address depending on the size of the variables and the constants. That's all what we are trying to write it in the form of algorithm. Just follow here. If there is a symbol in the label field, if you have a symbol, means in the left hand side of the mnemonic, then you search in the symbol table whether the symbol is already appearing. If there is an entry in the symbol table, yes, then it is an error because the same label is appearing more than once. This is not a. If not, then put the label as well as its location counter value, that is what is the address, into symbol table. This is what is the thing. If this is not the case, if it is not a label, then if search for the octave for opcode, then it should be an instruction. If instruction, fine. Then we'll going to add 3. Every instruction in SIC machine is 3 bytes. So we're going to increment it by 3 bytes if it is an instruction. For example, LDX 0 is an instruction. That is 3 bytes. So we're going to increment the location counter value by 3 bytes. So first we just saw the start. After that, we have seen that the starting address is given. If yes, we initialize the location counter. Then we have seen whether the label is appearing. If label is appearing and whether it is appearing in the symbol table, then it is an error. If not, make an entry of that label into the along with this address into the symbol table. Then we see whether there is an opcode and the opcode is there in the opcode table. If yes, then it is an instruction. We incremented the location counter by 3. Apart from this, there are some 4 more possibilities. That's what is written in this else if, this part. What are they? One is character constant, character variable, integer constant, integer variable. Right? See there. If opcode is equal to word means then it is an integer constant. Then obviously one integer constant will going to consume 3 bytes. So we added 3 to the location count. If the opcode is equal to RESW, then it is an integer variable. So integer variable size may be 1 word. One integer variable is 1 word. So how many integer variables you want? It depends on that. If you have an array of 100 integer variables, 100 into 3, that means 300 bytes supposed to be reserved. So that's what is being told. If opcode is equal to RESW, 3 into multiply 3 into the value, operand value, then that many bytes is supposed to be allocated, right? If not, opcode is equal to RESB, that is character variable. Each character variable consumes 1 byte. So if you have 10 character variables, 10 into 1, so 10 bytes need to be used. So that's how it is being done. If the opcode is equal to byte, then the byte may be an hexadecimal constant or it may be a character constant. It may contain only 1 character or it may contain 10 characters or any number of n number of characters. So for that reason, the size of that constant need to be measured and of that length of the constant should be measured. Then that many bytes should be added to your location counter. For example, if at all I have written H, byte, C and hello world. Hello world consumes 10 bytes. So 10 bytes will be incremented to your location counter. This theoretically telling you this once we do the implementation of assembler to pass 1 and pass 2, things will going to be easy. Fine, that's what is the thing. Rest of the thing is if nothing works, then you set an error flag and after that you need to write it into an intermediate file, because after the definition pass, every statement would have all the addresses and we don't need to have the non-executable statements. That means your declarative statements to be present in your next means should go for processing in pass 2. Only the symbol table entries will going to go. So for that reason, after implementation means after pass 1, whatever the outcome comes, that will be written into an intermediate file and that file will be taken for processing in pass 2. Got it? So this is the end of your pass 1. In pass 2 of the assembler, anyway not asked, I'll going to brief you out the algorithm, that's it. Pass 2 of the assembler should do the translation. What it does, now declarative statements will not be there, majority of your assembler directives will not be there. Don't need to worry about all those things. Just take each instruction, take the mnemonic, refer in the opcode table. If there is an entry, convert your opcode means your mnemonic to the hexadecimal opcode. What the idea? Convert the mnemonic to hexadecimal opcode. And operand, search in the symbol table, you will get the address of the operand. Replace the operand name by the address. If it is a constant, you should replace the name by its, sorry, if it is a constant, you should replace the operand by its value. That's what is the implementation of pass 2 of the 2 passes. So among this, pass 1 of a 2 pass assembler is a most widely asked, most have the high probability of appearing in the examination. Fine. So data structures of 2 pass assemblers as well as the pass 1 of the 2 pass algorithm will going to be most widely asked. Fine. Okay. Let's now go for the implementation part of your what you call 2 pass assemblers, right? So here we show the implementation, or we can understand the implementation of 2 pass assemblers by seeing one program. It's an SIC assembler, remember, not an SIC XC assembler, SIC assembler, and this is the program what we are using. What is the program? Your program should read 10 bytes of data from an input device, 1 byte at a time, one byte at a time. So it should read 10 bytes, and after reading each byte, it should store it into a string variable or a character variable string. So first byte is read, stored in str1 of 0, second byte is read, stored in str1 of 1, so on, till all the difference. Why this program is chosen? Because we have a loop here, we have a label here, and we have a index addressing modules, all possible variations. Means in your exam also, an entire program may be given and maybe asked for assembly, or a small code piece can be given and you may be asked for doing the assembly. So these are the possible questions. So either of these questions which I have asked, told important, may appear with this particular thing. Sure concept. I think new is going to appear, right? So what is that being asked here is, this is the program what we'll be using. Have a look at this. We have first column telling the instruction number. This is for our reference, nothing to do with your assembler, just to refer which row, which instruction does. Next is a label, any label that is appearing, mnemonic, operand. These are the things. First, let's look at the declaration. At line number 9, we have declared an input device, and we have given it a unique identification number F5, which is an hexadecimal number. Fine. And after that, string 1 is declared, which is of supposed to be 10 bytes. Sorry, there I have written it as 20 bytes. String 1 is a character variable of 10 bytes. Mind that there will change it. Count is a word. Word means an integer constant whose value is right now 10. And 0 is also an integer constant whose value is right now 0. This is the program. And see from the beginning, line number 1, we are telling name of the program is a string, and we are using assembler directive start, and we are giving an address 1000. So this is absolute assembly. In relative assembly, don't give the address there. Assembler by default we're going to consider the assembly address to start with 0, right? Like this. Yeah, see the line number 2. I'm telling LDX, load X register with 0. 0 is a constant whose value is right now 0. That's what is be loaded onto your X register. Next instruction is test device, in device. You are testing the input device. As I told you, we are using program controlled IO, wherein the responsibility of the program itself to check whether the input device, output devices are free or busy, and then wait and then go back and look again. This thing. So we are checking TD in device, testing the input device. If the result is EQ, JEQ, means if the conditional code set is 00, then the device is busy. So we go back to the previous instruction itself, that is in loop. You can see that label in loop is present at instruction number 3 or row number 3, right? If that is not the case, means if the conditional code set by your TD is not equal 00, then we go under read in device, RD in device. So we'll read the device, and means 1 byte or 1 character is read from the input device, and that will be placed onto your accumulator. So next instruction in line number 6, what we are doing is STCH. The character that is present in accumulator is stored into str1 of x, str1 comma x. It is an indexed addressing mode here. str1 comma x means string 1, and x is right now containing 0. So if you look at it, str1 of 0. But that's the instruction number 6. In instruction number 7, what we are trying to write is TIX count. What TIX does, I told you already. TIX increments the contents of X register by 1. The incremented content of X is compared with the specified address. That is your count. Count is how much? 10. You can see in line number. Count is 10. X is incremented. Earlier it was 0. X has now become 1. Is 1 equal to count? So conditional code will be set. If it is equal 0, 0, if it is less than, greater than, equal, like that. So the next instruction at line number 8, what we are writing is jump less than. Means if the TIX instruction conditional code is indicating that the X contents is less than the count, then we should go back to loop. Where is our in loop? It is at line number 3. We'll be repeating this. Next time, we'll read one more character from the input device and store it in str1 of 1, next str1 of 2, str1 of 3, so on. Until when? Until X becomes 10. When X becomes 10, your TIX will going to not set the conditional code to less than, but it will set the conditional code to 0, 0. So we'll be stopping the program. That's all. So 10 bytes is read from the device and it will be placed out to the string. Simple. Okay. Next we proceed. We go to the pass one. This is our pass one. As I told, pass one is a definition pass one. See there. First instruction, nothing is done because it is a assembler directive. It is telling that start of the program and you should use the address 1000 absolute assembly, right? For that reason, so from 2 onwards, all the instructions are given the address starting from 1000. And remember, as your opcode is also hexadecimal, your addresses will also be hexadecimal, right? So we may need to use, we must use hexadecimal addresses only. 1000. First instruction, that is LDX, is given 1000, and every instruction is 3 byte. So the next instruction, TD, getting the address 1003, and this is the second column is now the location counter. So the definition pass, location counter was initialized to 1000, next 1000, 1003, 1006, so on we are going. You can see that at the fifth instruction, the address is given is 1009, and the sixth instruction becomes 1000C. Why? After 9, 10 is A, 11 is B, and 12 is C, right? Like that, because it's a hexadecimal representation. And 7th is 100F, and 8th is 1012, and 9th is 1015. And here we can we constantly incremented the location counter value by 3 because all of them were instructions. All of them were instructions. So see, please observe and clearly have a look at row number 9, wherein the address is 1002. Right? But important thing is, see the next address. In device is a character constant. Any character constant, here the character constant is consuming 1 byte. So for that reason, the next address is not incremented by 3, but it is incremented by 1. 1015, the next address is 1016. Please similarly have a look. str1 is a character variable. Character variable where its size is 10. So for that reason, after str1, next address is going to be 1026, means 10 bytes is reserved for str1. Getting the idea? 10 bytes is reserved for str1. Count is a word. Word means integer constant whose value is right now 10. So count is getting the address 1026, but the next address it is next address 0 is getting is 1029 because every integer constant consumes 3 bytes. So for that reason, all the declarative statements are allocated address based on the size of the variable or the constant. This is what is the important thing to be observed in pass one, right? So we are not doing anything with the symbols that is appearing on RHS. That is in the column of operand. Nothing is. We are allocating the addresses for all the things that is appearing on LHS of your program, right? This is the end of pass one, wherein we defined the addresses for. In pass 2, we are supposed to convert all the mnemonics to its opcode, hexadecimal opcode, and all the operands to its addresses, and finally write it into an object code. That's what is the next task. So how about doing the pass 2? That we're going to see it in the next class. So because we have already crossed the time limit, so we'll be ending it here. Thank you. Thank you for joining.